Hello everyone. Hi. Hello. Okay. Hi. 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 And good afternoon to everyone. Okay. And today we are going to start a new chapter. So in the last class we were discussing about thermodynamics, right? So that was a recap of thermodynamics, and we will be taking the recap of thermodynamics after a few later. I think the recap will start again in September. So we'll be taking recap of all the chapters that has been finished in the standard by September. Okay. So during that time, we will start the recap of thermodynamics as well. So today we are going to start the new chapter, and this is the first chapter that you will study in 12th standard, right? Okay. So have you guys studied this? Have you guys completed solid state in your school curriculum? Okay, fine. So today we are going to start solid state, and before I start this chapter, I would like to tell you something about the chapter. That what are the things that we are going to learn in this chapter? Okay, you don't have it in any book. Okay. Yeah, it is there in every 12th standard syllabus, right? So whether it is CBSE, ICSE, or any other syllabus, so it is there in each. Okay, you are in 10th. Exactly, it is in 12th, right? So this is a 12th standard chapter. Okay, fine. Yeah. So today we are going to learn about the solid state, and in the chapter we are going to talk about different types of structure that exist in solid state and different types of crystal that we have, right? So we'll be talking about amorphous solid and crystalline solid, and then in crystalline solid we'll be discussing about different types of crystal structure that is possible, and different types of solid that can exist, right? So these are I have to cover in this chapter. Now let's start from the first line. So what is solid state? The solid state, or a state of matter having a definite shape and volume, is called solid state, right? So what is the difference? Can anyone tell me what is the difference between solid and liquid and gases? So how can it differentiate between the states of matter, the classical states of matter? By their molecules or by the arrangement of their molecules, right? So if you have, by the packing of the molecule, you can define whether it is solid, liquid, or gases, right? So okay, through diffusion. So there are various things, there are various parameters, or there are various properties looking at which you can differentiate between solid, liquid, and gases. So let me give you a brief idea about the different properties that is there in the solid state. So solid state have a definite shape and definite volume. Now it is having a definite shape and definite volume because the molecules of solid are very closely packed, right? That is, the intermolecular space between the molecules of solid is very less, right? Or you can see the intermolecular force of attraction in the solid is also very high, and that is why it is having a definite shape and definite volume. Now these are the various characteristics of solids. The solids have high density and high rigidity, it has negligible compressibility, and solids have definite shape and volume. Solids have low kinetic energy of particles, short intermolecular distances, and strong intermolecular forces, right? Now, solids are having high density because the molecules of solid are very closely packed. Now, if you are considering a structure where the molecules are very closely packed, then the mass contained in a unit volume will be higher, right? And if the mass contained in a unit volume is higher, that means you can say that density is higher, right? Solids have high rigidity as well. So you can't deform solids by applying force, right? And it has high negligible compressibility. So if you want to compress a solid by applying some amount of force, you won't be able to compress it, right? Because there is very little intermolecular space remaining after the packing of solid molecules, right? Solid molecules or atoms in case of elements, right? Now, every solid has a definite shape and volume, and the kinetic energy of the particles inside the solid is very less. In fact, in solid, the particles can only vibrate at its own position, right? So you won't see the flow of particle in the spaces in a solid state, right? So particle can only vibrate at its position in solid state. So that's why it has low kinetic energy of particle. Now, what can you say about the kinetic energy of, so how can you compare the kinetic energy of solid, kinetic energy of particles in solid, liquid and gases? So what is the differences in kinetic energy of particles in solid, liquid and gases? Can anyone tell me? So which of the state has highest kinetic energy of particle? So it's gases, right? So gases have highest kinetic energy of particle, and then the least kinetic energy of particles are in solid state only, right? Now, so you all would be aware about why kinetic energy of particles in solid is lesser, right? Plasma. Plasma is non-classical state of matter. So here we are not concerned with the non-classical state of matter. We are going to discuss about the solid state mainly, right? Okay. Is it clear? Plasma and Bose-Einstein condensate are non-classical state of matter. Now, in this chapter, we have discussed about solid state only. Okay, fine. Solid state have shorter intermolecular distances and it has a strong intermolecular force. So whenever two molecules are placed very closely, then the intermolecular force between those two molecules will be higher, right? And this is what is occurring in solid state. So in solid state, two molecules are very closely placed. Hence the intermolecular force between the molecules of solid is higher. Right? Now, solids can be classified into two parts. One is amorphous, another is crystalline. Now, what is the difference between amorphous and crystalline? So, amorphous solid are those solids which are having random arrangement of molecules inside the solid state. Right? So, it is irregular. You can say that irregular in terms of arrangement of molecules or arrangement of particles inside the solid, right? So if you have irregular arrangement of molecules, then in that case, what can you say about the properties, like about the physical properties inside the solid state? Crystalline is regular, right? Crystalline have a definite arrangement of molecule, but amorphous does not have a definite arrangement of molecule. Now, in case of amorphous, so if we talk about the properties like density and electrical conductivity and these type of property, if we talk about the physical property inside the amorphous state, then the physical properties physical property inside amorphous state is seen in different directions, right? So if you go in different directions, you will observe that the density in amorphous state is remaining same in all the directions, right? Yeah. So it has same value of physical property in all the direction. Yeah. So that is why we can say that amorphous solid are isotropic in nature, right? Now, in case of crystalline solid, the physical property changes in different directions. So you will observe different physical property in different direction. So is glass a type of fluid? Because I find it thicker at bottom edge and old window panes. Yeah. Yeah. You are true about it. So glass is a super cooled liquid, right? So if you cool the glass, if you cool the the heated molten silica particle suddenly, that gets converted into glass, right? Now glass are super cooled liquid, so that's why when you leave it for a longer period of time, you will observe that the bottom of the pane, so you will observe bottom of the glass becomes thicker, right? Okay, is there any other question? Crystalline are anisotropic in nature, right? Definite heat of fusion and amorphous, right? So we are going to discuss about all these in the next slide. Now let's discuss about all the properties that are present inside the amorphous solid. So you will observe irregular shape of amorphous solid because the molecules are arranged irregularly, and the order in case of amorphous solid is very short ranged order. That is, if you are observing a pattern inside the amorphous solid, you won't observe the pattern for a longer range, right? So there will be some pattern for a short range, and then it will be followed by a different pattern or some random arrangement of molecule, right? So this is what you will observe in case of amorphous solid. Now amorphous solid is it is isotropic in nature. Now, what is the meaning of isotropic? So, isotropic means if you go in different direction, the physical property remains same in case of amorphous solid. This is the meaning of isotropic nature. Exactly. It is called pseudo-solid. Yeah. Now, what is the melting point of amorphous solid? So, if you will observe the melting point of amorphous solid, you will observe a range of melting point. So, the melting point in case of amorphous solid is not sharp, right? So, you won't observe the sharp melting point in case of amorphous solid. Now, if we draw a graph let's say we are drawing a graph between temperature and volume. Let's say we are representing temperature on this axis and volume on another axis. Is mercury a pseudo-solid? See, mercury is, so if you are converting the mercury into a solid state, then you will have to decay. So melting point of mercury is very less, right? So you will have to go below the melting point of mercury. Now, if you have super cooled the mercury, then it will be amorphous in nature. Then you can call it pseudo-solid, right? And if you don't have the super cooled mercury and you have cooled it slowly, then in that case mercury will exist in crystalline state in solid form. Is it clear? Is it clear, Subish? Yeah. So if you are cooling a liquid slowly, then in that case you obtain a crystalline solid, and if you are cooling it suddenly, then you obtain a amorphous solid, right? Now, Atashi has also asked some question. Electrical property depends on direction measured. Sorry, I am not able to understand the question. What is the question, Atashi? Depends on the direction measured. in case of amorphous, right? So electrical property will, if you are observing the electrical conductivity in case of amorphous solid, so it will change in different direction, right? So you will observe different conductivity of the solid, different electrical conductivity of different electrical conductivity in different direction in case of amorphous solid. Now let's say you are observing the phase transformation in case of amorphous solid, then the volume of solid state is minimum. And let's say if you are increasing the temperature, right, then the volume of solid changes. So the change in volume will be very less, right? You won't observe a large change, right? This is how, if you are increasing the temperature, the volume will change slightly, and then the solid will start converting into liquid state, right? Now here, in this case, if you are considering the graph for amorphous solid, then in that case you won't observe the same state during the phase transformation, right? So in this case, the volume of, so when the solid will start converting into liquid, so it will, the volume of, so volume, in this case, the volume will not remain constant. Let me draw the graph. So volume will increase, and volume increase. Sorry, just give me a second. Let's represent the temperature here and volume on the other axis. And in that case, you're increasing the temperature, the volume rises, then the increase in volume is rising. After certain temperature, there is sharp rising, right? So this is how the graph is in case of amorphous solid, right? Now in case of crystalline solid, if you are observing the straight chain in case of crystalline solid, then you will observe that the temperature, so as you increase the temperature, the volume of the solid increases. The increase in volume of the solid is lesser, right? And when the phase transformation takes place, then in that case the volume remains constant, right? During the phase transformation in case of crystalline solid, the volume remains constant, and then the volume of, so when the liquid, when it gets converted into liquid, the volume start rising, and then when the liquid gets converted into gaseous state, then also you will observe that the volume will remain constant as long as the liquids get converted into gaseous form, right? But this is not the nature in case of amorphous solid. So you will observe, just give me a second. Yeah. Okay. So is it clear? Is the graph clear to you? Sorry about the line that has been drawn here. Not able to remove it. Is the graph clear to everyone? Is this graph clear to everyone? How the phase transformation will take in amorphous solid? Okay. So in case of the, so as you would have studied about the phase transformation in case of solid state. So whenever the phase transformation takes place, so in case of crystalline solid, you will observe that during the phase transformation, the volume remains constant. So let's say you are converting a solid, so let's say you are increasing temperature of a solid. Now if you are increasing the temperature of a solid, then there will, so at the melting point, the solid will start converting to liquid state, right? But when the solid will convert into the liquid state, so at that temperature, the volume of the solid remains constant, right? So the volume remains constant, the temperature remains constant. The volume will change, the temperature remains constant. Okay, just remove everything. I'm going to draw a new graph, right? Okay, I'm drawing the graph again. So I am drawing the graph for crystalline solid first. So in case of crystalline solid, this is how the graph is. The temperature remains constant, not the volume. And this is corresponding to volume, right? So if you are observing the change of a state, then there will be solid state, and if you start heating a solid, so the volume of the solid will increase, and at a particular temperature. So this temperature is corresponding to melting point, right? So at melting point, you will observe that the temperature is not increasing, but the volume will increase. So the solid in this state, at this point, there will be solid and there will be presence of solid and liquid both, and above the melting point, you will observe liquid state, right? So this is the graph corresponding to conversion of state in case of crystalline solid, right? Why amorphous solid melt over a range of temperature? Now amorphous solid melt over a range of temperature because the properties, because it does not have the same kind of bond, right? In case of crystalline solid, you will observe the similar bond. So every bond in case of crystalline solid is almost similar, right? So all the bond will start breaking at the same temperature in case of crystalline solid. But in case of amorphous solid, there are different types of bonding existing, or you can say there are different types of force existing inside the amorphous solid, right? Now, if you are trying to convert the amorphous solid into liquid state, you need to break different types of bond inside the solid, right? So that's why you need a range of temperature to break all the types of bond. Is it clear? Is it all clear? Yeah. Now, in case of amorphous solid, you won't observe a sharp melting point, right? So there will be a range of temperature in which the melting of solid will occur, right? So this is the graph in case of amorphous solid. This graph is corresponding to amorphous solid. And above graph is corresponding to crystalline solid. Is it clear? So is both the graph clear to you now? So you will observe a range of melting points. So in this temperature range, the melting of amorphous solid occur. Is it clear? So this is the meaning of sharp melting and boiling point, right? Okay. Now the next property is heat of fusion is indefinite. Now the meaning of this is, in case of amorphous solid, you will find indefinite heat of fusion. Heat of fusion is the heat which is required to convert the solid into the liquid state, right? So in case of amorphous solid, you can't be certain about the heat of fusion required in different amount of amorphous solid that you have taken, right? So that's why we can say that heat of fusion in case of amorphous solid will be indefinite. Is it clear? Is this point clear to you? That heat of fusion will be indefinite. Heat of fusion is the amount of heat which is required to convert a liquid state, a solid state into liquid state, right? Now, since amorphous solid are not ordered, or you can say the molecules in the amorphous solid are not arranged, so it does not have a particular arrangement. So that's why if you will take different amount of amorphous solid, then corresponding to different amount of amorphous solid, you may need to supply different amount of energy to convert that solid into liquid state, right? So that's why you can't be certain about the heat of fusion. So heat of fusion is always defined in terms of amount of heat required per kg or per gram, right? So a specific amount of matter, so it is corresponding the heat required to convert a specific amount of solid into the liquid state. So that is called heat of fusion. Now, if you are taking, let's say, if you are taking 1 gram, two different sample of 1 gram sample of amorphous solid, right? So 1 gram sample of amorphous solid not necessarily take equal amount of heat to convert from solid state to liquid state. So this is the meaning of indefinite heat of fusion. Now is it clear? Ash, is it clear? Okay. So I'm showing you what is the meaning of indefinite heat of fusion. So heat of fusion is not definite. That means what? Let's say this is the amorphous solid, and in this solid the molecules are arranged randomly, right? Now if from this solid you are taking two different 1 gram sample, then 2 different 1 gram sample from same amorphous solid may not necessarily require the equal amount of heat to get converted into liquid state, right? So there is a possibility that amount of heat required to convert this 1 gram solid into liquid state is Q1, and the amount of heat required to convert this 1 gram sample into liquid state is Q2. So there is a possibility that 1 gram sample of the same amorphous solid can have different heat of fusion, right? Or it can require different amount of heat to get converted into liquid state. Is it clear to everyone now? What is the meaning of indefinite heat of fusion? So you can't define a definite heat of fusion for amorphous solid. Is it clear to you? Okay. Go to the next point. Next point is the nature of amorphous solid is pseudo solid or supercooled liquid. So usually amorphous solid is formed after supercooling the liquid state. That is the cooling in case of the cooling of liquid state, liquid in this case should be sudden, right? So if you are cooling a liquid suddenly, then it is called supercooled liquid, and amorphous state is found in supercooled liquid. Is it clear? Right? So do you have any doubt about the amorphous solid? Do you have any doubt in any of the property? Fine. So let's go ahead. Now another part of the solid, so another type of solid is crystalline solid, and in crystalline solid the shape is it has a definite geometrical shape. That is, the molecules are arranged properly inside the crystalline solid. So there is a definite arrangement of molecule inside crystalline solid, right? Molecule or atom. Now the order of crystalline solid is long range. So it is long range ordered solid, right? So you will observe a particular pattern of molecule for a long range inside the crystalline solid. Yeah, crystalline solid is anisotropic in nature, and Ash, what is this? What have you typed here? Ash, what is this? Can you explain me? Typed by mistake. Okay. Fine. Okay, fine. So Parul has asked the question, why cooling suddenly induces amorphous character? See, when you are cooling a liquid state suddenly, then what happens? The temperature of different position decreases at different rate, right? So that's why, so you are not giving an opportunity for the liquid particle to arrange properly, right? So the liquid particle gets converted into solid state at different time when you are cooling it suddenly, right? Is it clear? So the amount of heat withdrawn from different position will be different. Okay. So let me tell you what anisotropy is. I'm explaining it to you by graph. Okay. So let's say you are talking about, so in case of crystalline solid, so if there is a crystalline solid, so in case of crystalline solid, you will observe, just give me a moment. Let's say this is a crystalline solid, right? Now, if you are looking at crystalline solid, then in crystalline solid, you will observe a definite pattern of molecule, right? So there will be a definite pattern of molecule in case of crystalline solid, right? Say this pattern is definite. Now, in case of amorphous solid, the molecules will be arranged randomly, right? And if a pattern is existing, the pattern will be existing for a shorter range. It will not be a long range pattern, right? Now, in this case, so there are certain physical property defined for every solid, right? Now, physical properties like density, electrical conductivity, refractive index. So, if you are talking about these physical property, then in case of crystalline solid, let's say you are going into a particular direction, then in this direction you will observe different value of density at different position, right? So, you won't observe the value of density to be same across the whole crystalline solid. Right? Let's say you are looking at the density, then density of the solid will be different at different position. You will observe a certain value of density at this position. So if you are considering a unit volume across a different position inside the solid, let's say you have considered a unit volume at this position and a unit volume at this position. Then at both the position, you can observe different density, right? Such type of solid is called isotropic in nature, right? This is isotropic because it is having same value of physical property across. This is anisotropic. It's not isotropic. This is anisotropic in nature, right? Such solid is called anisotropic in nature, right? What are isomorphism? Now, this is called isomorphism. So, isomorphism. So, isomorphism is something else. So, if there are two particles having similar structure, then those particles are called isomorphous in nature, right? So, if there are two particles having same molecular formula, then also they are called isomorphous. So they should have a particular arrangement. So if there are two solids having the same molecular arrangement, then those solids are called isomorphous, right? And for two solids to be isomorphous, it should also have the same molecular formula, right? So CaSO4 and MgSO4 can be isomorphous in nature, right? CaSO4 and MgSO4. Right? So these two are having similar molecular formula, so that's why they can be isomorphous in nature, right? Clear? Okay. Now, in case of amorphous solid, you will observe that in a particular direction, the value of density will be same, right? So if you are considering two unit volume at two different positions, then you will observe the same value of physical property at the two position. Clear? Why crystalline are anisotropic even they have regular shape? So if they have regular shape, let's say you are considering unit volume, right? So there is a possibility that so let's say you are considering this as a crystalline solid. Okay, I'm showing you why it can have different property, right? Let's say you are considering a unit volume and the value of so let's say this is a unit volume that you are considering, right? You are considering this as a unit volume. Now in a unit volume you are observe, so you are in this unit volume, how many molecules are there? So these dots are representing the molecules. So how many molecules are there? How many molecules are present in this unit volume? Can anyone tell me? So how many molecules can you see here? 4, right? Now we can draw this unit volume at some other place, and in that unit volume there is a possibility that instead of 4 there are only 2 atoms present, right? So we can draw the same unit volume like this as well, right? So same unit volume can contain different number of molecules, right? So in a ordered arrangement, same unit volume can have different number of molecules. Is it clear to you? Is it clear? Yes. So same same volume. If same volume are having different number of molecules, so what can you say about the density? The density of the two volume will be same or different. The density of the two unit volume will be same or different. It will be different, right? So that's why the crystalline solid will be anisotropic in nature. Clear? So that's why it is anisotropic in nature. Now, if the molecules are arranged randomly, then in that case, the number of molecules that you will find in a unit volume at different position can be different, can be same, but in most of the cases it will be same, right? Is it clear? So in this case, if you are going in a particular direction in case of amorphous solid, then you will observe, so here the molecules are arranged randomly, right? So in this case, you will observe that you will find a same number of molecule in different volume, right? So that's why it is isotropic in nature. Is it clear? Can we go ahead? Yeah. So these are the difference between crystalline solid and amorphous solid. Now you will observe a sharp melting point in case of crystalline solid, and the heat of fusion of the crystalline solid will also be definite, right? So we'll observe a definite heat of fusion in case of crystalline solid. Now heat of fusion is definite in case of crystalline solid. Why? So how can you see that heat of fusion will be definite in case of crystalline solid? I've just told you. So heat of fusion depends on what? It depends on the kind of bond which is existing inside the molecule, right? So in case of crystalline solid, there are similar kind of bonds. Yeah. So that's why the heat of fusion has a definite value in case of crystalline solid. And why it is having a sharp melting point? Sorry, so the reason for sharp melting point is also the same, that because the same kind of bond is existing, and heat of fusion is definite because different volume of the different unit volume will be having a definite different unit mass will be having requiring same amount of heat to get converted into solid to liquid state. So that's why we can say that heat of fusion is same, or heat of fusion is definite, right? Okay. So is this 2 point clear to you? Why melting point is sharp and why heat of fusion is definite? Yeah. Now crystalline solid are also called true solids. crystalline solids can be divided into molecular solid, ionic solid, metallic solid, and covalent solid. Right? Now, molecular solid are those solid in which the molecule cannot get converted into any other form. Right? So, if you are we have various examples corresponding to different types of solid. Right? Now, molecular, so let's talk about molecular solid here. So, molecular solid can be further divided into non-polar, polar, and hydrogen bonded solid. So, non-polar solid, so carbon dioxide is so if you are considering carbon dioxide solid, then carbon dioxide solid is a non-polar solid. There can be polar solid as well. So, ice, if you are, polar solid, NaCl solid is a polar solid, right? And hydrogen bonded solid can be there. So ice crystal are hydrogen bonded solid, right? So so whenever the molecule is not getting dissociated into any other form and it is intact inside the solid, then that solid is called molecular solid, right? How can we come to know a solid is crystalline or amorphous? But by looking at the molecular formula. So amorphous, in case of amorphous solid, you won't have a definite formula, right? So by looking at the molecular formula, you can't say. So molecular formula of the there is a possibility that molecular formula of amorphous and crystalline solid can be seen, right? So you can't say by looking at the molecular formula whether the solid is crystalline or amorphous. Is it clear? So by looking at molecular formula, you can't say that. Parul, is it clear? Is the question clear? Is it out clear? So by looking at the molecular formula, you can't say whether a solid is amorphous or crystalline, right? Because same molecule can be present inside the amorphous solid and same molecule can be present inside the crystalline solid as well. So it depends on the process that you are using to convert liquid into the solid state, that whether the solid will be amorphous or crystalline. So if you are cooling the liquid slowly, then in that case you obtain the crystalline solid, and if you are cooling the same liquid suddenly, then in that case you obtain the amorphous solid, right? So by looking at the formula, you can't say whether the solid is amorphous or crystalline. Is it clear, Parul? No, the molecular formula would be, so by looking at the molecular formula, you can't say. So there are certain rules to identify the types of solid. So we will discuss about it. So let's see, so that is there in the coming slide, right? So this is your molecular solid. Now I'm going to speed up. So now all of you are aware about the type of solid, right? So, all of you are aware about what is crystalline solid, what is amorphous solid, right? Now in crystalline solid, so we are discussing about the different types of crystalline solid, right? Now first type is molecular. So in molecular solid, the components are molecule. Molecular solid can be divided into non-polar, polar, and hydrogen bonded solid. A non-polar solid molecular solid has certain feature. Non-polar molecular solid are soft. It is insulator of electricity, right? So it is not a very good. It is not a conductor of electricity because it does not have the free electron, right? So that's why it is an insulator. Now it has very low melting point. So the melting point of molecular solid is not very high because it does, so if you will consider the ionic solid, then so we are talking about the non-polar solid, right? So in case of non-polar molecular solid, you will observe that there is no bond, there is no dipole attraction between two molecules, right? So if dipole attraction is not existing between the two molecules, then melting point will be low. That is, it will get converted into liquid state from solid state at a very low temperature. CCl4 is non-polar. Yes, CCl4 is non-polar. Right. Because the dipole moment of CCl4 is 0. Clear? Okay. Now, so what can we say about the intermolecular forces? So, intermolecular forces that will exist between the two molecules will be dispersion and London force, right? So, dispersion force of attraction exists between the two molecules in case of non-polar molecular solid, right? And the examples of non-polar molecular solid are neon. So if you are converting the neon gas into the solid form, that is, you can convert the neon into solid by decreasing the temperature of neon. Now, if you are considering the solid form by a neon atom, then that will be called as non-polar molecular solid, right? And CO2 is also non-polar molecular solid. CO2 is non-polar molecular solid because the dipole moment in case of CO2 is 0, right? Now H2 is also a molecular solid. So whenever you are having a molecule which is having whenever you are having a molecule which are having dipole moment equal to 0, then that will always form non-polar molecular solid. Now polar molecular solid are also soft, and again polar molecular solid are also insulators of electricity. Now this solid is containing some ions. So not ions. So a polar molecular solid will be having some polar nature. So it will be having some dipole moment, but it won't be able to conduct electricity, right? Because for conduction of electricity you need free electron or some charge carrier. The charge carrier can be ions, right? But in this case you don't have any ion. Clear? And neither there is any free electron. So that's why it won't conduct electricity. Clear? Now the melting point of polar molecular solid is also low, right? So it does not have very high melting point because the bond in this case can be broken easily, right? So the dipole force of attraction that will exist between the molecule in case of polar molecular solid is weak and it can be broken easily. So that's why it has low melting point. And example for polar molecular solid are HCl and SO2. Right? So whenever there is some dipole moment between the molecule, and if you are converting that molecule into the solid form, then that solid will be polar molecular solid. Right? If polar, non-polar and hydrogen bond are insulators, then molecular solid are insulators. Yes, molecular solid are insulators. True. Right. So molecular solid will always be insulator. Clear? Is it clear? Yeah. Now hydrogen bonded molecular solid. So hydrogen bonded molecular solid are little hard. So it is harder than the other molecular solid. And in this case, it is again an insulator because this does not have any charge carrier again. And the melting point of hydrogen bonded molecular solid is also low. Because in this case also the bond can easily be broken between the two molecules because hydrogen bond is not a very strong bond. Hydrogen bond is a weak bond, right? So it can be broken easily. Now intermolecular forces here will be hydrogen bond, right? And example of this is H2O ice and NH3. Can anyone tell me that hydrogen bond exists between, so what are the different atoms between which the hydrogen bond is possible? So hydrogen bond can be formed by hydrogen with any atom, FON, right? So these are the atoms which can form hydrogen bond, because these elements are very electronegative in nature. So only highly electronegative element can form hydrogen bond, right? Yeah, so HF and H2 are having hydrogen bonding inside it. Now example of hydrogen bonding molecular solid is H2O ice and NS3. Right? Now a question has been given you, which of the following solutes will form a molecular solution with water? Can anyone answer? So which will be the solid which will form molecular solid form a molecular solution with water? So you have to tell me which will form molecular solution. C. So everyone is getting C, right? Yeah, C will form molecular solution. Now it will form molecular solution because in this case it won't get dissociated into ions, right? So CH3OH methanol will not get dissociated into ions when you will dissolve methanol into water, right? So it will exist in the molecular form only. And if you will dissolve any other compound, that is AlCl3, AgNO3 or KMnO4, then that will get dissociated into ionic form. So it will form cation and anion inside the water, right? Now this is the only, so C is your correct option. Now crystalline, another type of solid is ionic solid, right? Now in case of ionic solid, we have ions inside the solid, right? So cation and anion is present inside the solid. So ionic bond is existing between the ions in case of ionic solid. Now melting point of ionic solid is high, and ionic solid are hard but brittle in nature, right? So ionic solid like NaCl is hard but brittle in nature, right? Constituent particles in this case are ions. So example of this is NaCl, Mg or ZnS. So if you will see all these solids, so in this case you will observe a cation and an anion, right? So in case of NaCl, Na plus and Cl minus will be there in the crystalline solid, and which is also called crystalline. So it is called ionic solid also, right? So it is a part of crystalline solid. Here. Now the fourth point is attractive force lying between the species inside the ionic solid is Coulombic force or electrostatic force of attraction, right? So whichever force is existing in the electrovalent bond, so that force lies in the ionic solid. Here, so electrovalent bond has electrostatic force of repulsion. So that's why ionic solid is also having the electrostatic force of attraction. So that's why ionic solid is also having electrostatic force of attraction, or there will be repulsion also between the two similar type of ions. Here, which chemical property decides whether solid is brittle or malleable? So brutality and malleability is not a chemical property, it is physical property, right? Now brittle and brittlity and if you are ductility and malleability, you can say. So ductility and malleability is not chemical property, it is physical property. Okay. Now if you are so let's say you are trying to strike a particular substance with a hammer, then if the substance break into pieces, then it is called brittle in nature. And if you are able to beat that particular substance into a thin sheet, then that is called malleable in nature. So these property depends on the bulk of the particular substance or bulk of the matter, right? So that's why it is physical property, it is not chemical property. Okay. Next point is conduction of electricity. So ionic solid is also an insulator. Now in this case, the ions are present inside the solid, but those ions are not mobile, right? So they are not, so they can't move from their position. So they are not the charge carrier in this case. So that's why ionic solid is also an insulator, right? So insulators, conduction of electricity. Insulators in solid state, but conductors in molten state and in aqueous state. Now, if you convert the ionic solid into molten state, let's say you are heating the ionic solid and it gets converted into the molten state, then in that case, the ions become mobile, right? And when the ions become mobile, they become a charge carrier. Yeah. Ions are free to move in molten state, true. So that's why it becomes a charge carrier and then it starts conducting electricity. Here, ions, so ionic, so if you dissolve the ionic solid into the water, then it also gets broken into cation and anion. So again, in case, so if you are talking about aqueous solution, then in that case also we have ions which are acting as a charge carrier. So that is also conducting in nature. Water is molecular solid, still it conducts electricity. Sorry, so if we are talking about, so water conducts electricity in its liquid state, right? Yeah, so it conducts electricity in its liquid state. It does not. Yeah, so water. So if we talk about the pure water, so that won't be capable of conducting electricity, right? So pure water won't conduct electricity. Here. So only so it conducts electricity because of the presence of some ions inside the water. Yeah. Okay. Fine. Now, example of ionic solid are NaCl, MgO, and ZnS. So all the ionic compound forms ionic solid. Right. So these are forming ionic solid. Now a question is there, why are ionic solids electrical insulator in their solid form? So we have already covered it. So can anyone tell me why? No free ions, right? Or free electrons. Right. So that's why they don't conduct electricity and they are insulators. Yeah. So because of the absence of free electron or ions which are movable, yeah, there are no charge carrier, you can say. That's why they are insulators. Right. Now another metallic solid is another part of crystalline. So another type of crystalline solid. And in metallic solid, so these are the properties, these are the features of metallic solid. Now in metallic solid, the melting point is fairly high, right? So metallic solid has fairly high melting point, right? See, in case of molecular solid, the force of the bond which was lying within the molecular solid was either dispersion force or hydrogen bonding or dipole-dipole force, right? In case of metallic solid, you will observe a metallic bond, right? And metallic bond is stronger than the dipole-dipole interaction or the dispersion force, right? Metallic bond. The bond which is existing between the two metal atom is called metallic bond, right? So, is it clear? So there is a bond between two metal atom as well, and that bond is metallic bond. Yeah, so when metals are arranged in the solid form, how is it different from others? Now, see, in case of you already have studied about three different types of bonds, right? One is electrovalent bond, another is covalent bond, and there is metallic bond, and the fourth one is coordinate. So fourth one is van der Waals. So bond which is existing. That is not the real bond. So there is a van der Waals force of attraction between the two molecules as well. So this is how these are the force of attraction which can lie between the particles, right? Now, in case of metallic bond, so if you will observe a metallic bond, in case of metallic bond, two metal atom touches each other, and these two metal atom has several force of attraction between them, right? So the nucleus of one atom will be attracting the electron present on the other atom, and the nucleus of other atom will be attracting the electron present on the other atom, right? So, but this is a special type of bonding because in this case the two metal atom touches each other, right? So whenever you will see the arrangement inside the metals, metallic crystal, so you will observe that the two metal atom are touching each other. So this type of bond is called metallic bond. Now, in case of dispersion force, the dispersion force or the van der Waals force lies between two neighboring molecules. If you are considering, let's say, you are considering two carbon dioxide molecules, so in that case, so I'm representing the carbon dioxide molecule like this. So there will be one oxygen atom attached. There will be two oxygen atom attached to carbon dioxide molecule, right? So such will be the type of carbon dioxide molecule. Now the force of attraction lying between the two carbon dioxide neighboring carbon dioxide molecule is called van der Waals force of attraction or London force of attraction. Clear? Now the force of attraction between the two molecules will be weaker than the metallic bond. Is it clear to you now why it will be weaker? Because this force will be higher. What does ductile mean? So ductility is the property by which a metal can be drawn into wire. Right. Okay. Now, and the melting point is fairly high in case of metallic solid. Now, nature of the solid is hard, malleable, and ductile. So, when metallic solid are hard, malleable, and ductile, right? So you can you can beat the metal into a thin sheet, and you can also draw the metal into a thin wire, right? So these are the property of metallic solid. Now, attractive force lying between the metallic solid is metallic bonding, right? So there exists metallic bonding between the two metal atoms in case of metallic solid. Now, conduction of so metallic solid are able to conduct electricity in solid state and molten state, right? So it conducts. So are good conductors in solid and molten state. So see, these are carrying. So it is good conductor in solid and molten state because it contains free electron inside the metal, right? So there are free electrons inside the So that's why they are able to conduct electricity due to presence of free electrons, right? And it can so if it is conducting electricity in the solid state, it can also conduct electricity in molten state, right? Now, example of metallic solid are all the metals are arranged in. So all the metals individually will form metallic solid. Clear? Now another is covalent solid. Now in this solid you will always also called network solid, right? Now in covalent solid you will observe covalent bonds only, right? And covalent solid have high melting point, and the constituent particle in case of covalent solid are atoms, right? So usually, the atoms are so all the atoms present inside the covalent solid are covalently bonded, right? Now, nature of the solid is hard. So all the covalent solid are hard in nature except graphite. So graphite is a covalent solid which is not hard in nature, right? And why is it not hard in nature? Can anyone tell me? So there is a speciality in the structure of graphite due to which it is not hard in nature. Yeah. Layer structure. Very good, Shivani. Very good. Because it has a layered structure, and the two layers are bonded by Van der Waals force of attraction, right? So that is why it is not hard in nature, right? So it is, yeah, parallel layer. So there are lots of parallel layer inside the graphite. And how many bonds are present between the carbon atoms in case of graphite? Can anyone tell me? There are three bonds. Very good, very good. So if there are three bonds, one of the electron in case of carbon is free, right? So if one of the electron in case of so in case of graphite you have one free electron in carbon, then should it be conducting or should it be non-conducting in nature? Should it be conductor or insulator? Conductor, right? So graphite is conductor because of the presence of free electron inside it, right? And so that is what we observe here. So now if we talk about other covalent solids, so covalent solid are usually insulator because of the absence of free electron, except graphite because graphite is having a free electron with carbon. And the attractive force lying in case of covalent solid is covalent bonding. Example is SiO2, quartz, SiC, diamond and graphite. So these are covalent solids. So you will observe covalent bond between each and every atom present inside the covalent solid, right? So in case of Si2, there will be bond existing between Si and all the Si and O atom present inside the covalent solid, right? There will be no other types of bond. That is, there won't be any Van der Waals force of attraction, right? Or any other type of bond. Clear? Okay. Now we have to classify these substances into types of solid. Now, so I'm starting from the first solid. Now, magnesium oxide is what kind of solid? Is it molecular solid, ionic solid? Magnesium oxide is ionic solid, right? So, magnesium oxide is ionic solid, right? This is ionic. What about diamond? Diamond is covalent, right? Silver? Silver is what kind of solid? Metallic, right? This is metallic solid. What about ice? Ice is what kind of solid? It is molecular solid, right? And in molecular solid, it will be in which category? It will be hydrogen bonded molecular solid, right? So it is molecular. What about brass? Brass is an alloy, but it is containing only metallic bond inside it, right? So that's why it will be metallic solid, right? What about fluorite? Fluorite is CaF2. So fluorite is what kind of solid? It is ionic, right? What about quartz? Quartz is what kind of solid? So we have just studied it is a covalent solid. And sucrose? Sucrose is what kind of solid? It is molecular solid. Right? Yeah. Molecular and non-polar solid. Okay. Now, what is crystal lattice? So, crystal lattice are let me show you what crystal lattice is. So these are the characteristic of crystal lattice. So each point in a lattice is called a lattice point or lattice site. Now each lattice point represents one constituent particle, and lattice points are joined by straight lines to bring out the geometry of lattice. Now let's say you are considering a solid. Let's consider a metallic solid. So in metallic solid, you will observe a definite arrangement of atoms inside the solid, right? Now, so solid, you define a crystal lattice, right? And a lattice point is, so these all the points shown here are called lattice point, right? And these are the characteristic of lattice point. That lattice point are, each lattice point represent one constituent particle, right? So when you are representing, so the point here, so every point represented here are lattice point, and the dot is representing a particular molecule, or you can say part, right? So this is called crystal lattice. So is lattice clear to everyone? So what lattice is? Yeah. So every lattice point will be corresponding to a particle inside the solid. Okay. Now what is unit cell? So a unit cell is the smallest portion of crystal lattice which when repeated in different direction generates the entire lattice, that is entire crystal. So this is the unit cell. Now if you will repeat the unit cell in different direction, you will obtain the whole crystal. Here, this is the definition of unit cell. So it is the smallest portion which when repeated give the whole crystal. Here, dimension along 3 edges. Yeah. So if you are exactly, so you will have to repeat or you will have to extend the unit lattice along the 3 edges to get the whole crystal. Here. Yeah, it has 6 parameters, and we'll discuss about the parameters. And these are the 6 parameters of crystal lattice, right? So the 6 parameters are the side. All the 3 sides are the parameter of unit cell. These are of unit cell. So there are 6 parameters of the unit cell. The 3 sides of the unit cell are 3 parameters, and these 3 angles which has been represented here are the other 3 parameters. So there are 6 parameters of the unit cell. Clear? Is it clear? So all these parameters are clear to you? Now if you change any of the parameter, so you will observe different types of unit cell if you will keep changing the parameters, right? Now there are now unit cell can be divided into 2 different parts. One is primitive unit cell and another is centered unit cell. Primitive unit cell is that cell where primitive unit cell. In the primitive unit cell, particles are present only at the corners, right? And in case of centered unit cell, you will observe particle present at other positions as well. Yeah. So in primitive unit cell, particles are only present at the corners of the cell, right? And in case of centered unit cell, you will observe particle at the corners and there will be particle at other positions as well, right? Centered unit cell can be subdivided into body centered, face centered, and end centered, right? Now, body centered unit cell is that unit cell where the atoms occupy corner places. What is face centered? I will tell you what is face centered unit cell as well. So, in the body centered unit cell, you will observe atoms occupying position, and there will be one atom at the center position as well. Now here the atoms shown are not touching each other. In this case, you will have to imagine that atoms are touching at the body diagonal, right? So if we are talking about body centered unit cell, So in that case, you will have to assume that these atoms are touching each other along the body diagonal. Clear? It is an open structure. Okay, which part do you want me to explain again, Ash? Can you tell me? Body, okay. So body-centered, we are talking about body-centered unit cells. So body-centered unit cells are that unit cell in which the atoms occupy the corner side, and there is one atom at the center of the cube as well. So this is lying at the center of the cube. So you will have to imagine a three-dimensional box, and there is an atom which is lying at the center of the three-dimensional box, right? So such type of cell are called body-centered cubic cell, right? So this cell is body-centered cubic. Here, okay. Now in the body-centered cell, in the body-centered unit cell, you will observe that the atoms are touching each other along the body diagonal. Here, is it clear to you? Okay. Shivangi had asked about open structure. Shivangi, what is open structure and closed structure? So these all are. So every structure, every structure represented here. So the boundary which is represented in the unit cell is not the real boundary, right? So this is not a boundary which is actually existing. So these are representing. So actually, you will observe several molecules or several atoms arranged inside the solid. Now we are trying to identify the lattice position in it. Now there is a process of identifying the lattice position. So whenever you define a lattice position, you have to make sure that all the atoms, all the lattice position are having similar type of arrangement around it, right? So here in case of body centered, you can take any of, so all the atoms will be having similar arrangement around it, right? Now this atom will be acting as a body center for other 8 atoms, right? This atom will also act as a body center for other 8 atoms. Now this atom will also act as a body center for other 8 atoms. If you are extending the whole crystal, right? So if you are extending this unit cell in all other direction, you will observe that each of the atoms which are represented here will act as a body-centered atom for a particular unit cell, right? So every atom has similar type of arrangement when we describe the lattice. Clear? Is it clear to you? Is it clear what I just said? So every atom are having similar arrangement around it, right? Okay. Now face-centered, so another type of unit cell is face-centered unit cell. And in face-centered unit cell, one particle lies at the center of each face and one particle lies at each corner, right? So one particle will be lying at each face in case of face-centered. And in case of face-centered, the atom, so these 3 atoms will touch each other, right? So in case of face-center, you will observe that the atom lying on the 2 corners and the face center will touch each other, right? So let's say this is the atom which is lying at the center of the face, then it will touch the atom, the size of the atom represented as same here. So you will have to assume that the size of atoms represented here are same, right? Okay. So same atom has been represented here. Okay. So this is how the atom will touch each other in case of face-centered cubic cell, right? Now, if these atoms are touching each other, can you tell me what will be the relation between the radius and the edge length of the unit cell? Can anyone tell me what is the relation between radius of the atom and the length of edge of the unit cell in case of face center? 4r is equal to root 2a, right? So how can you see that? So this distance, it is this triangle is a right angle triangle, right? So the triangle that I am representing here is a right angle triangle, and the side and the value of base is a, and the value of height is also a. Then in that case, the value of hypotenuse will be root 2a, right? Root 2a is equal to 4r, right? This is the relation between the radius of the atom and the edge of the unit cell in case of face center. What is the relation between radius of the atom and the edge of the unit cell in case of body center? Can anyone tell me what is the relation between radius of the length of the edge and radius of the atom? 4r is equal to root 3a, right? So everyone knows about it, or do I need to explain it? I can explain it how it is coming out like that, right? Okay. Let's see. Let's consider this to be the unit cell. And in the unit cell, I am considering this distance to be the body diagonal, right? This is the body diagonal. Now, I already told you that the atoms in case of body-centered cubic cell will touch along the body diagonal, right? Now, if you can find the length of the body diagonal of a cubic cell, so I'm considering it to be a cubic cell, right? So in this case, the length of the value of length, breadth, and height will be same, right? This will be a, this will also be a, and this is also a, right? Now, what will be the length of body diagonal? So you can find the length of body diagonal, and it will come out to be root 3a, right? Root 3a is the length of body diagonal in this case. You can calculate that as well. So how can you calculate the length of the body diagonal? So you can do that. Right. Okay. Yeah. So you can so you can calculate the length of the body diagonal. Let's say this is. How can I do that? I'm just showing you. Let's say this is the cell. Now I'm drawing the face diagonal here. So let's consider this to be the face diagonal. Right? This is the face diagonal, and this is how the face is there. Now, what is the so you can calculate the value of face diagonal. So, what is the value of face diagonal? Face diagonal is equal to root 2a, right? So, the value of face diagonal is root 2a, right? Now, you have a right angle triangle, and the right angle triangle is this triangle, right? So, the triangle that has been shown here is a right angle triangle, right? This angle is 90 degree, and in this right angle triangle, the value of base is root 2a, and the value of height is how much? So in this right angle triangle, what is the value of height? It is a, right? Now, if you have to find the value of body diagonal, so that will be equal to how much? So it will be root 2a square plus a square under root, right? So this is the length of body diagonal, and it is equal to how much? So this will be equal to root 3a, right? So this is the length of your body diagonal, and this should be equal to 4r. Here, this is how you can find the relation between the edge of unit cell and the radius of atom. Here, does in phase center one particle lies at the body center even apart from one at the faces? No. In case of phase center, you will always find one particle at the phase center only, right? So there is no particle at the body center. Here. Okay. So we have covered phase center. Now another type of unit cell in the centered part is end-centered. And end-centered unit cell is that unit cell where one particle lies at the center of any two opposing faces and one particle lies at each corner, right? This type of unit cell is face-centered unit cell. So there are two particles which is lying at any of the two face center, and other particles are lying at the corner. Here. Now these are the types of primitive unit cell. So primitive unit cell can be there are 7 primitive unit cell. One is cubic, tetragonal, orthorhombic, monoclinic, trigonal, and triclinic. Now, these unit cells differ in the 6 parameters that we have for the unit cell, right? So there are slight difference parameters in the 6 parameters. Okay. A cubic cell is that cell where the axial distances are equal. That is, here the size, the value of length, breadth, and height are same, right? And the angle is all the angles. All the angular parameters, all the axial angle is also equal to 90 degree, right? Okay. Now, tetragonal is a unit cell where so it is almost similar to cubic cell, right? So it is almost similar to cubic primitive cell, and but the only difference is in this the height is different from length and breadth, right? So A is equal to B, but it is not equal to C, and all the angles are 90 degree only. No, it is not known as cuboidal. So when we are discussing about this this type of structure in solid state, then it is called as tetragonal, right? Now another type of primitive unit cell is orthorhombic. In case of orthorhombic, all the axial distances are different, right? So A is not equal to B, and that is not equal to C. So so that is, you can remember it. Length is not equal to breadth is not equal to height in case of orthorhombic primitive unit cell, right? And all the angles, all the axial angles are equal to 90 degree only, right? Okay. Now, monoclinic is another type of primitive unit cell. In this monoclinic structure, you will have different values. So all the axial distances are different from each other. And in this case, there are two angles which are 90 degree. That is, you will observe a rectangular plate in this case. So this, so let's say alpha. So here it is given that alpha and gamma are 90 degree. That means this angle and this angle are 90 degree, right? So these are two rectangular plates. Now beta is not equal to 90 degree. So beta can have any other angle, right? So this side will be slightly tilted, right? Now if beta is different, what can you say about this angle? So let's say beta is 120 degree. So what will be the value of this angle? Can anyone tell me? What will be the value of the angle that I have represented? So you have to find the value of the angle, this angle. I have given that beta is equal to 90 degree, 120 degree. So it will be 60 degree, right? Okay. So are you able to imagine the 3D structure here? So that what will be the 3D structure if A is not equal to B is not equal to C and alpha is equal to gamma is equal to 90 degree and beta not equal to 90 degree. So is the structure clear to everyone? Yeah. Now another type of primitive unit cell is hexagonal unit cell. In hexagonal unit cell, you will have so you will have a hexagon, and a structure will be over the hexagon. So this is a hexagonal plate. So this plate is a hexagonal, right? This is the top view of the hexagonal unit cell, right? And this is the bottom face. Okay. This is the top face of the hexagonal unit cell, and this face is the bottom face, right? So it is a hexagon, and in a hexagon you will observe. So you will have the value of A to be equal to value of B, right? And the value of C is not equal to A and B. So this length, so height of the hexagonal unit cell is different from the sides. Here. Okay, Vikram is having some problem with the network. Okay, if someone is having problem with the network, can try to log out and log in again, right? Yeah, so that is the only thing that I can suggest as of now. I will see what can be done about it, right? So is it a network problem on your side, or is it so is there any problem with the platform? I think there will be network problem on your side only, right? Okay, fine. So let's go ahead. Now trigonal or rhombohedral unit cell is there. So in case of trigonal or rhombohedral unit cell, you will have all the sides are equal in this case, and two angles are equal, and one of the angle, so two angles, all the angles are not at 90 degree, right? So in this case, the value of alpha is equal to beta is equal to gamma, but all the angles are not equal to 90 degree, right? So all angles are equal to each other, but not equal to 90 degree, and the sides are equal to each other. Here, in case of rhombohedral. So this is another type of primitive unit cell. Now triclinic is that unit cell where the lengths are not equal to each other, but angles angles are also not equal to each other, and they are not equal to 90 degree as well. So such type of unit cell is called triclinic unit cell. Clear? Okay. Now see, So we have talked about 7 primitive unit cell. Now primitive unit cell is that cell where atoms are occupying only the corner side, right? So we are talking about the primitive unit cell. So there are 7 different types of primitive unit cell. In this primitive unit cell, so we can have different Bravais lattices, right? Now in cubic lattice, in okay. So in case of cubic lattice, we can have primitive structure as well, and we can have a body-centered cubic lattice too, and we can have a face-centered cubic lattice too. Why end center is not there in cubic cell? See, that structure is not possible in cubic cell, right? So whenever, so as I told you, so whenever you decide a lattice, so while deciding the lattice, you have to take care that every atom is having similar type of arrangement, right? So that is possible in orthorhombic only. So if you are considering n-center orthorhombic, then in that case you will observe that every atom is having similar type of arrangement, right? But in cubic lattice, if you are taking the n-centered case, then in that case you won't observe similar type of arrangement and similar type of arrangement for every atom present inside the lattice, right? Is it clear? Yeah, so it does not exist. So centered in cubic lattice does not exist. So these are the only 3 possible lattices in case of cubic cell. Is it clear? In case of tetragonal in case of tetragonal cell, you can have primitive cell and body-centered cell, right? So if you have tetragonal cell, then in that case you can have primitive structure or body-centered structure. Yeah, so these are the 2 structures possible in case of tetragonal cell. In case of orthorhombic cell, so what was the property of tetragonal cell? So in tetragonal cell, we saw that the 2 sides were equal and one of the side was not equal and all the angles were at 90 degree, right? So in such cell, there are the 2 structures. There are these 2 structures possible. In case of orthorhombic, so in orthorhombic, all the lengths were not equal to each other, but the angle was equal to 90 degree. All the angles were equal to 90 degree, right? Now, in such a structure, you will observe every kind of lattice. There will be primitive lattice, there can be body-centered lattice, there can be face-centered lattice, there can be end-centered lattice. Is it clear? Okay. Yeah. Monoclinic lattices are so there can be primitive lattice and end-centered lattice in case of monoclinic cell, right? So in what was clinic? So in monoclinic we had the 2 angles were equal to 90 degree and one of the angle was not equal to 90 degree, right? And this primitive cell will be there and end-centered cell will be there. Now, in case of hexagonal lattice, you will have in case of hexagonal lattice, you will always have only primitive cell, right? There are different lattices shown here, right? Okay, you are still facing the internet problem over it. The network problem is huge on your side, I think. See, you just have to bear for more 15 minutes more. Okay. So in 15 minutes, I think the whole slide. So we will be able to cover what we have to cover in this lecture, right? So it will take only 15 minutes. Fine. Yeah. So that you can do, Vikram. You can try resetting your connection. You try to log out and log in again. And if it is still not working, then there would be some problem with the network on your side, right? Okay. So now again, so different lattices has been shown here, right? So trigonal lattice is like this. So it will contain a primitive lattice only, right? In case of trigonal cell, and triclinic cell will also contain primitive lattice only, right? Now there is a process of calculating number of atoms inside the unit cell, right? So how can you calculate the number of atoms present inside the unit cell? So let's say you are considering a simple lattice, a primitive cubic lattice, or the simple cubic lattice. So in primitive cubic lattice, what you have is so you have So in simple cubic lattice, all the corner atoms, all the corner sides are occupied by atoms, right? This is the case of simple cubic cell, right? Now, what is the process? You can't say that this cube is containing 8 atoms, right? So can you see that this cube is containing 8 atoms? So how many atoms are contained inside the cube? So what can you say about that? So okay, don't read the statement that has been written above. So okay, fine. You can calculate that, right? So you can't see that number of atoms present inside the cube is 8. So you will have to calculate that how many atoms are present inside the cube. So how can you do that? So for that, atoms at the corner contributes 1 by 8 to the unit cell. Now, how can you find out with what is the contribution of a particular atom in the unit cell? So for that, you will have to cover. So you can identify the fraction contributed by looking at how many cubes are required to cover the whole atom, right? So if let's say you have to find out the contribution of this atom in one cube, then you should find out that how many cubes are required to cover the whole atom. Right, so there will be so you will require 8 cubes to cover the whole atom, right? So 4 cubes in the plane of this atom only, right? So in the plane of this cube which has been shown, so you will require 4 cubes in this plane and 4 cubes above this plane, right? So you will require 8 cubes, total 8 cubes to cover this whole atom, right? So that's why you can say that contribution of this atom in one cube is how much? So that is equal to 1 by 8. So always the atom at the corner will contribute 1 by 8 to the unit cell, right? And an atom on the face contributes 1 by 2 to the unit cell. Now can you find how can you find out how much is the contribution of atom at the face center? So again you will have to do the same thing. Now to cover the atom which is present at the face, how many cubes are required? So you require 2 cubes to cover the whole atom which is present at the face center of the cube, right? So if 2 cubes are required to cover the whole atom, that means the contribution of one atom to the unit cell will be equal to 1 by 2, right? Okay. An atom at the body center contributes singly, that is 1 to the unit cell. Now, so the atom which is present at the body center is completely present inside the cell, right? So that's why the part contributed by that atom is equal to 1. So it is contributed the whole. It is contributing the whole atom to the unit cell, right? So contribution corresponding to atom present at the body center is equal to 1. Yeah, 2 atom in total. So if you have to calculate the number of atom present inside the BCC structure, right, body centered cubic structure, then in that case the number of atoms atom present is 2, right? Okay. Now, so here we are calculating the total number of atom present in primitive cubic unit cell, and total number of atom in one unit cell will be equal to, so there are 8 corner atoms, and 1/8 atoms per corner, 1/8 atoms per unit cell is contributed by the corner atom. So the total number of atom will be equal to 8 multiplied by 1/8, which is 1, right? Now, in case of face-centered cubic unit cell, the total number of atom will be equal to, so there are 8 atoms which are present at the corner, right? So there are 8 atoms at the corner, and there are 6 atoms present on the 6 faces, right? So, the number of atoms contributed by atoms at the corner will be equal to 8 multiplied by 1/8. Right, so this will give you the number of atoms contributed by atoms at the corner. Now, number of atoms contributed by atoms present at the face center will be equal to 6 multiplied by 1/2 atom per unit cell, right? So the total number of atom per unit cell is equal to 4 in this case, right? So you can always remember it. So if you are considering face centered cubic unit cell, then in that case the number of atom present at a face center, so number of atom contributed inside one unit cell is 4, right? Very good, very good. Yeah, so this is what is going to happen with body centered cubic cell. So in body centered cubic cell, there are 8 atoms which are present at a corner of the cell, and there is one lying at the center of the unit cell, right? So number of atoms contributed by corner atoms to the unit cell will be equal to 8 multiplied by 1/8 per corner, right? And there will be one, so, and the number of atom contributed by atom present at the body center of the unit cell will be equal to 1. So the total number of atoms present inside the body centered cubic unit cell is 2, right? So you can also remember this, that the number of atoms present inside the body centered cubic unit cell is 2. Now a question is given to you. You have to solve this question. In end centered, okay, so how many atoms, you tell me how many atoms will be present in case of end centered? 2, right? Everyone is getting 2. So end centered is what? So I'm drawing the end centered unit cell first. Assume it is an orthorhombic structure. So in orthorhombic structure, what do you have to consider? So in orthorhombic, A is not equal to B is not equal to C, and all the angles are equal to 90 degrees. So end center exists only in case of orthorhombic structure, right? So in case of end centered cubic cell, you have one atom. So there will be 2 atoms at the face center, at the 2 face center opposite to each other, right? And there will be 1 atom at each corner, right? This is the end centered cubic cell, right? Okay, this is your end centered cubic cell. In the end centered cubic cell, there is 1 atom at each corner, and there are 2 atoms lying at 2 opposite faces, right? So in this case, total number of atom will be equal to, total number of atom is equal to, there are 8 atoms at the corner, so number of atoms contributed by atoms at the corner is equal to 8 multiplied by 1/8 plus, now there are 2 atoms present at the face. So what is the contribution of atom towards one unit cell which is present at the face? So contribution is 1/2, right? Now since there are 2 atoms which are present at the face center, so number of atom contributed by atoms at the face is 2 multiplied by 1/2, and this is equal to 2. Here? Okay, so you have to solve this question. So has anyone solved it yet? Okay, I'm going to remove this. So has anyone solved the question yet? Or do you have any clue? Yeah, number of atom is same in BCC and ACC. Number of atom present in the cubic cell in a unit cell is same. Okay. So I'm giving you a hint. So the question is calculate the number of unit cell present in 3 gram of sodium, right? Can you calculate the number of sodium atom present in 3 gram of sodium? Yeah, you can do that way as well. Parul, you can calculate the mass of one unit cell and you can then divide that by the mass of sodium sample that you have taken. So there are different methods that you can use. So you can use either of the method. You can first calculate mass of unit cell and then you can divide the given mass by the mass of one unit cell, right? That is one way. Another way is you can calculate the total number of atom present inside the sodium sample that is given to you. And once you have calculated the total number of sodium atom, you can find the number of unit cell by dividing the number of sodium atom by number of atom present inside one unit cell, right? So either of the two method can be used. 46. Umakant is getting 46. I don't think 46 is the right answer. You can express the number of unit cell in terms of Avogadro number if you want to, because I think Avogadro number will be used in this case. Do you want me to solve it? 0.39 multiplied by 1 to the power 23. It can be correct. Yeah, it can be the answer. Fine. I'm showing you one method. Okay, I will show you both the methods. First method is you can calculate the total number of atom present in 3 gram of sample. Now total number of atom of sodium present in 3 gram of sample will be equal to how much? It is 3 divided by 23. This is the mole of sodium, right? So 3 divided by 23 is the mole of number of moles of sodium, right? That is 10, not. Yeah, it is 10. Yeah, I got it actually. It's not 1. It's 10 to the power 23, right? Fine. So this is the number of moles of sodium atom. Now, if you divide the number of moles with Avogadro number, you can find the number of atoms of sodium present in the given sample, right? Now, this is the number of sodium atom present in the given sample. Na is Avogadro number. Na is Avogadro number. So this is the total number of sodium atom present. Now number of atom present in number of sodium atom in one unit cell is equal to how much? So it is given that the sodium atom is in BCC lattice, right? So number of sodium atom in one unit will be equal to how much? Can you tell me? Number of sodium atom present in one BCC in BCC structure will be equal to how much? So it is 2, right? 2 atoms will be present inside one unit cell in case of BCC structure, right? Now total number of sodium atom is given to you, is known to you, and number of atom present in one unit cell is known to you. So number of unit cell can be calculated. Number of unit cell is equal to how much? This is 3 divided by 23 into Avogadro number, right? This divided by 2, right? So this will give you the number of unit cell, and this is equal to how much? You can calculate the value. So it is coming out to be how much? So whatever the value comes, Can you do the calculation after this? Yeah. You can use other way to calculate the total number of unit cell. The other way is you can deal with the mass, right? You can directly deal with the mass. You can find the mass of one unit cell. So mass of one unit cell will be equal to how much? So 2 multiplied by 23 mu, right? This is the mass of one unit cell, and 23 mu can be written as 23 multiplied by 1.66 into 10 to the power minus 24 gram, right? So I have converted the AMU into gram, and then you can calculate the number of unit cell by dividing the given mass by mass of one unit cell, right? This cell, and this will be equal to 3 upon 2 multiplied by 23 into 6.11 into, sorry, not 6.11, 1.66 into 10 to the power minus 24, right? So both ways you can obtain the number of units, right? Okay. Fine. Let's solve another. So is the question clear to everyone? Is both the approaches clear to everyone? What is the weightage of this chapter in JEE? See, so you cannot be certain about the weightage because the weightage of every chapter changes every year, right? So you should not think about the weightage at this time, right? At this period of time. Just cover all the syllabus, and weightage can always change. So weightage of any chapter can change, right? So it is possible that too many questions can be asked from same topic in IIT JEE, right? So you should be prepared about each and everything that is there in the syllabus, right? Okay. Now, can you solve this question? What is the formula of a compound having a cubic structure formed by element A and B, in which the atoms of A are present at the corners and atoms of B are present at the face centers of the cube? AB3. So everyone is getting AB3, right? Yeah. Okay. So it is saying that so this is, let's say this is the unit cell. Now in this unit cell, all the corner atoms are occupied by atom A and B are present at the face center of the cube, right? Now if all the corner atoms are occupied by A and B is present at the face center of the cube. These are, so every face center is having one B, right? So these are the face center atom. Now number of A atom will be equal to how much? So number of A atom will be equal to number of A atom inside the cube will be equal to 1 by 8 multiplied by 8. 1 by 8 is the contribution and there are 8 atoms of A. So this is equal to 1, right? And number of B atoms inside the cube will be equal to how much? So there are 6 atoms of B which are present at the face centers. So number of atom will be equal to 1 by 2 multiplied by 6 is equal to 3. So the formula of the compound will be A, B, C, right? Okay. So everything that we have studied up till now is clear to everyone. Okay, fine. So now we will continue this chapter in the next class, and we will read about different types of words that are present inside the lattice. So there is tetrahedral word, octahedral word, there is triangular word. So we'll talk about that, and then we will calculate the different packing fraction existing inside the cube. This chapter is easy, right? Ash, is it confusing? So which part is confusing for you? See, I don't think that anything is confusing there. The only point is, if you are not able to imagine the 3D structure, then you might feel a little difficulty in understanding about it. Yeah, it's all about 3D imagination, right? So if you are able to imagine everything in the 3D structure, then it becomes easy. Yeah. You should be able to imagine the 3D structure, right? Okay. So crystal lattices, there are 7 different primitive cells, and Bravis lattice is crystal lattice only, right? So there is no difference in crystal lattice and Bravis lattice, right? Sorry, Bravis lattice or Bravis lattice, whatever you call it, right? There are 14 Bravis lattices, and all are crystal lattice only. Clear? Is it clear to everyone? So, okay, yeah, fine. So we will start how to study organic chemistry. I mean, the animation. First, I can tell you how to study organic chemistry, right? So if you have started studying organic chemistry, then you should be aware about all the mechanism of different reactions, right? So every mechanism should be clear to you, right? Then only you will be able to understand each of the named reaction properly, right? So first focus on the reaction mechanism. Try to understand it properly, and there is geometrical. There is a general organic chemistry chapter. So you have to be thorough with the general organic chemistry chapter if you want to understand it properly, right? The concept of resonance should be clear to you. When hydrogen bonding is occurring, that should be clear to you, right? And then if you want to remember the name reaction, then the mechanism of those reactions should also be clear to you, right? Is NCERT sufficient for preparation of JEE? See, NCERT covers each and every part which is there in the JEE syllabus. But if you want to be 100% sure, then you should follow some reference book as well. Yeah, this is what I believe. So everything which is there in the JEE syllabus is there in NCERT as well. But you need to have some reference book if you want to understand the concepts clearly, right? Pradeep Pradeep, is sufficient for 12th standard. Okay, if you want to understand the mechanism properly, if you want to read about the mechanism, then you can follow Morrison Boyd, because everything is explained clearly in that book, right? Foreign authors, yeah. So Morrison Boyd is there. JDD is for organic, right? Inorganic. JDD is for inorganic. You see, you can follow any of the book, right? It is not necessary that you have to follow the foreign author's book only. You can follow the Indian author's book as well. So, whichever book you are following, try to cover each and everything which is there in the book. So, at least cover one book properly before going into the examination. Yeah. So whichever book you are following, cover one particular book corresponding to every subject properly. Yeah. Morrison Boyd. Yeah. Morrison Boyd is good for organic chemistry. Concepts are very good. See, it doesn't matter whichever book you are. So whichever book you feel like you feel comfortable in, try to read that, right? So if you are comfortable in reading any particular book, and if you are able to understand that book properly or the language of the book properly, then follow that book. But cover each and everything which is there in the book, right? This is what I want to say, right? How many hours I have to study per day? When I was preparing, I never used to divide my time according to the subjects, right? I used to divide it according to the need of the subject, right? So there would be topics which will require more time. So during those topics, you need to devote more time to that. So let's say you are studying a particular topic. Let's say you are studying electrochemistry, and you are finding it difficult to understand electrochemistry. Then you need to devote more time on the electrochemistry. And at the same time, let's say a parallel topic in physics is going on, which is relatively easier, then you can devote lesser time on that topic, right? So you have to divide your time smartly, right? So so I can't define it randomly, right? So I can't say that you should have studied 3 to 5 hours every day chemistry, because there will be topics in physics which is going on simultaneously, and you might need to give more time to that topic, right? So always choose your time smartly, right? Okay, the test. So as soon as the lecture will end, so a test will appear, I think. And if the test is not there, it will come within few days, right? So don't worry about the test. You will get to write the test on every lecture, right? Yeah, exactly. Very good. So that's the point. You should be comfortable at your pace, right? You should not try to match any other person's pace. You should always study by your pace, right? Yeah. This is the general strategy that you should follow in life, right? Don't run behind any other person. Okay. Fine. Okay, all the best, students, and hopefully all of you get selected in the competitive examination that you are aiming for. Okay. See you in the next class. Okay. Yeah. Bye bye.